In this video, you're going to learn how to determine the minimum sample size necessary to estimate a true population proportion given a margin of error and confidence level. For our example, we'll use a margin of error of 5% and a 95% level of confidence. We'll start by reviewing the margin of error formula for population proportions. That formula is E equals the critical value of Z times the square root of P times Q divided by N. Since we're solving for N, we need to be able to establish values for E, Z critical, P, and Q. Note that in the problem, we're given a margin of error of 5%. We need to write this as a decimal, so we have 0.05 equals, and now we need to find our critical value of Z. To find our critical value of Z, we note that we're using a 95% level of confidence. There are a couple of ways that you can find the critical value given this information. You can use a Z table and find your values there, or you can use the inverse normal function on a graphing calculator. If you're using the table, it's pretty straightforward. You'll look for 95% confidence interval or confidence level across the top. And then for most tables, you can look along the far left column to find your Z-score that corresponds to a 95% confidence level. You can also use technology, which I recommend. So if we consider a 95% confidence interval, we need to find the critical value of Z at the interval's endpoints. Since the total area under the curve is 1 in a normal model for a Z distribution, I know that with 95% in the middle, I must have 5% left over. And since the model is symmetric, I must have the same amount in each tail. So 95% plus 5% give me 100%, which gives me my total area under the curve. You'll hear it referred to interchangeably as 1 and 100%. So I have 5% left over that needs to be split equally between the two tails. That means I need 2.5% in each tail. We can use our inverse normal function on the calculator for a TI-83 or TI-84. You'll hit your second key, then distribution, which is above the variables key, option 3, which is inverse normal. And since we're interested in getting the critical value of Z at these endpoints, we'll put in 0.025, the decimal form of 2.5%. This will give you negative 1.96. So at my left endpoint, I have negative 1.96, right endpoint, positive 1.96. We'll use positive 1.96 since at a certain point in this formula, we'll be squaring both sides, and whether we use positive or negative 1.96, we're going to end up with a positive result. That's our critical value of Z. Now for the square root of P times Q divided by N, Since we haven't been given information about P and Q, the expectation is that we default to 50-50. So 0.50 times 0.50, all divided by n. Now we need to use algebra to solve for n. So I square both sides. 0.05 squared on the left becomes 0.0025. 1.96 squared becomes 3.8416, and then that's times 0.50 times 0.50, which equals 0.25, all divided by n. Notice we've removed the radical, because any time you raise a square root to the second power, they cancel each other out. Next, we multiply 3.8416 by 0.25. So we have 0.0025 equals 0.9604 divided by n. And then using algebra, multiplying both sides by n, dividing both sides by 0.0025, we end up with n equals 384.16, and we'll want to round up to the nearest whole number. So we would say that the minimum sample size necessary to estimate the true population proportion, given a margin of error of 5% and 95% level of confidence, is about 385. So again, this is how we determine the minimum sample size necessary to estimate the true population proportion, given a margin of error and confidence level. I hope you found the example helpful, and we'll see you next time.